he is the originator of Chord's FPGA DAC system, creator of the Hugo, the M-Scaler, the Mojo, and of course now the Mojo 2,
sure.
which we're going to be hearing about today. So rather than take up time talking, I'm just going to pass it over to our presenter, Rob Watts.
Well, it's fantastic to be doing a Canjam again. Can you hear me okay back there? Okay. It's fantastic being able to do a Canjam again. I've been stuck in my cave at home for the last 2 years, not gone anywhere. In the UK, we couldn't travel anywhere apart from within the UK, and no one will want to really holiday in the UK because it's pretty awful. It's normally raining. And last summer was a dreadful summer. So I'm probably going to do a lousy presentation. So if I do a lousy presentation because I'm out of practice, then, apologies. But there we go. I'll do my best. So I thought before going into the depths of Mojo 2, I thought I'd do a little summary as to what I'm about, what I'm trying to achieve with audio, and what are the key features of Mojo, or the original Mojo. And then explain the benefits of Mojo 2. So what do I want from audio? What I want to achieve is the musicality. And by musicality I mean getting emotional, tapping your feet, wanting to listen to the music, wanting to listen to more music, getting that spine-tingling effect when things really work. And these things happen naturally when you listen to live unamplified sound. And I want to be able to recreate the emotional experience that you can get when you're listening to live sound. And that's what my passion is all about. I've been doing this for maybe too many decades. I started design work when I was 20, which is 40 years ago, over 40 years ago. And I think I've made quite a lot of progress, particularly over the last 10 years. And there's a lot of progress happening now. In fact, one of the benefits of COVID was that I've been able to do a lot of fundamental research work, which questions that I've been in my mind and not had the time to evaluate. So what do we want a DAC amp to do? Most designers, when they're designing a DAC, they're playing around with the sound. They might want to make something that sounds rich and warm, or they might want to make something that grabs you by the balls and is very sharp. And so they've got in their minds a particular type of sound. The trouble with that approach is every piece of music you play sounds the same. It's got that stamp on there. And that's not what you hear when you hear live music. So with live music, you could be playing a saxophone that's sounding very rich and full and smooth, and a trumpet at the same time that's very piercing and sharp. And I want my reproduced audio to be able to portray those variations in timbre, pitch, melody, dynamic, all those kind of things. And if you can portray variations, you'll get emotionally involved with music. So, what are the variations? Variations in timbre, variations in space, being able to define an instrument in 3 dimensions. Variations in dynamic, pace and rhythm, instrument separation, and that sense of instrument power. So when a trumpet goes off and it's 3 feet away from you, it's an incredibly sharp, aggressive, powerful sound. And at the same time, you may have something really sensitive and quiet playing, and in real life, you'll be able to discriminate those differences. When you listen to reproduced audio, that power and authority of a loud instrument gets quashed, and the delicate instruments become stronger than they should be. Being able to properly perceive the starting and stopping of notes. So that nice sharp edge. Digital audio is very poor at reproducing sharp edges. Things are often hard and aggressive or just unnaturally soft. So the only way of achieving these variations is with true transparency. There's often an artificial sense of transparency that people often define products as sounding transparent, but well actually it's a forced false presentation. It's not true transparency. So what are the technical factors that conventional DACs fail on? Noise floor modulation. And this changes your ability to hear, perceive refinement and accurate timbre. Small signal accuracy, small details, depth perception, that kind of thing. And then transients. And here we're talking about the WTA filter and the interpolation filter and recovering the timing of transients. What I'm going to talk about first is noise floor modulation and small signal accuracy. So noise floor modulation. All DACs create noise. And by noise I mean that hiss that you hear. The white noise. A tiny fixed noise is perfectly okay, because if you go into a concert hall and the air conditioning's playing, you hear that gentle little noise, it doesn't bother you because you can still perceive the music properly. The problem is when that noise gets modulated and increases with the music itself, and that's noise floor modulation, and that causes enormous subjective problems. Because the brain cannot separate the sounds out of some noise floor modulation and the sound of the original instrument. So imagine you're playing a saxophone, and the saxophone sounds rich and dark, and there's a white noise pumping up and down with the sound of the saxophone. The brain cannot separate out the sound of the white noise pumping up and down and the sound of the saxophone. It lumps it together because it's been modulated together. That means your saxophone, instead of sounding rich and warm and soft sounding, will sound bright and hard because of this extra noise pumping up and down. There's also another problem. Let's say you've got a saxophone playing and a trumpet playing at the same time. Both of these two instruments will create noise floor modulation. The noise floor modulation will be, some noise will come from the saxophone, some noise will come from the trumpet. And the brain is then getting a confusing situation. It's got the signal from the saxophone, the signal from the trumpet, and it's got this noise that is a mixture of the two. And so the brain then finds it quite difficult to separate those individual sounds out. So not only does noise floor modulation make rich, warm things sound artificially bright, it also blurs everything together. So being able to separate individual sounds out into individual entities, the brain's got problems with. What is also amazing about noise floor modulation is levels well below measurable levels are still audible. And that's why I'm very careful when I do publish the measurements. I talk about measurable noise floor modulation. All of my products have no measurable noise floor modulation. They do have some noise floor modulation, but it's not measurable. And the immeasurable noise floor modulation is still audible. And one of the research things that I've been looking at is to find out what the subjective limits are for noise floor modulation. And it turned out to be a number that was much, much smaller than I expected. Seriously small numbers. Anyway, that's a story for another day. Small signal accuracy. So, small signal nonlinearity. This is where if you've got a signal at the maximum output, 0 dB, and then you reduce it to, say, minus 120 dB, the DAC should have an amplitude of minus 120 dB coming out. But when you measure the signal itself, it won't be minus 120 dB, it'll be minus 121 or it'll be minus 119. There'll be a small signal amplitude error. This error is very important subjectively because it confuses the brain and it makes it difficult for you to perceive depth. So the more accurate the small signals are, the better the perception of depth becomes. Depth perception. So if you go into a cathedral, listen to an organ, You're 200 feet away, shut your eyes. The organ sounds 200 feet away. If you listen to an organ on your home stereo and play it, shut your eyes, it doesn't sound 200 feet away behind that wall. It'll sound, if it's good, maybe 6 feet away. If it's a normal, regular, high-end system, it'll be about a foot behind the speakers. So that perception of depth is a huge problem with reproduced audio. We don't get anything like the sense of depth that we can hear when you're wandering around and you hear a dog bark and the dog is 2 miles away. You know it's 2 miles away, it sounds 2 miles away. You won't get that from reproduced audio. And one of the reasons you don't get that perception of depth is because small signals are not being reproduced accurately enough. What I found is that if there is the smallest amount of error on this, you can hear it, and you hear it in terms of collapsing depth. And for ideal depth perception, I've got a technical test for this, and this is being able to reproduce minus 301 dB as a signal. Now, minus 301 dB is incredibly small, and when I've discovered that this level of sensitivity was important subjectively, I told myself, I cannot publish these figures because people will say, you're completely effing nuts, or you are a liar and a charlatan because you're trying to just pay people to buy products and you're coming up with silly numbers. And actually, I sympathise with that view because there are a lot of strange people selling things like diluted water that's better than non-diluted water and all that kind of stuff. But the thing was, I've done these listening tests and I've done it hundreds of times. And if it's not reproducing a minus 301 dB, you can hear it in that the depth is degraded. So I thought, sod it, this is what I'm hearing, this is what the evidence is. Science is not about theory, science is about explaining the evidence. And the evidence is clear from my point of view, so I decided I'm going to publish it. People criticize me, that's fine, I don't care. That's what I can hear. And I can hear it under blind conditions. So, conventional DACs, they won't even do 140 dB, let alone minus 301 dB. Pulse array. Now, pulse array was a DAC conversion technology that I invented in 1995, and I developed it to solve these two problems: small signal nonlinearity, getting small signals to be accurately reproduced, and to eliminate noise floor modulation. I won't explain how that happens because it's too complicated, but there are seminars where I do explain, the intricacy of that. It's an FPGA DAC, but the FPGA is not the DAC. The FPGA creates the digital signals, and it's flip-flops and resistors, discrete components, that does the conversion into analog. And it's the discrete components that does the conversion that is the big benefit, or one big benefit. In the past, I designed silicon chips for major semiconductor companies for audio. The major problem you have with silicon is substrate noise. So noise from the digital parts getting through onto the substrate, and then from the substrate to the mixed signal analog parts. That noise corruption causes immense problems, and it causes noise floor modulation. So having it as a discrete components to do the analog is a huge benefit. One big benefit is you don't have to do it differentially. You can make it single-ended. So the pulse array noise shapers are 1 billion times more capable in terms of resolving small signals than chip-based or conventional DACs. The analog side, because of the fact that the noise shaper runs at 104 megahertz, conventional noise shapers run at 3 megahertz, R2R DACs run at 768 or 384 kilohertz. The benefit of that is that we can have a very simple analog section because the analog filtering can be minimal. It's only got one amplifier, 4 components in the direct signal path, 2 resistors, 2 capacitors. That's 10 times simpler than a conventional DAC. And the benefit of reducing all those passive components, all those analog components, the op-amps, the amplifiers, is you get much better transparency. So I've briefly talked about noise floor modulation, small signal accuracy, and I'm now going to talk about transients and why transients is a problem, and that leads me on to the WTA filter. Transients is the number one problem with digital audio. And it's all about the timing of transients, because the timing of transients the brain uses to make sense of what we hear. What we hear is not our ears. What we hear is the brain processing the data that our ears are giving us. And audible is a complete constructed illusion that the brain has generated. It's not your ears, it's the brain generating an illusion. There's a huge amount of processing going on that we have no idea how the brain does what it does. We perceive pitch from transients. So bass, for example, if we remove transient information from a bass guitar, you cannot follow the pitch of the bass. Soundstage from transients. So the difference in timing between the left ear and the right ear, that helps locate instruments from left to right. Timbre is important from transients. Remove the transient of a piano and a trumpet, you cannot tell the difference between the sound of the piano and the sound of a trumpet. It's unrecognizable. And these are psychoacoustic tests that people have done for many years. Of course, starting and stopping notes, that is a transient. So when you want to hear that nice, sharp, leading edge sound, that's transients. Digital audio's Achilles heel is about the reproduction of the timing of transients. We've got, with CD, one sample, 22 microseconds later, we've got another sample. The DAC has to work out what's going on from one sample to the next sample, because your transient will probably be somewhere in between. It might be there, it might be there, it might be there, and it's got to work out where those transients are actually occurring. That's the job of the interpolation filter. The problem is conventional DACs do not do a good job at reconstructing the timing of transients. And so they have a lot of uncertainty on the timing of transients. So sometimes transients are a little bit early, and sometimes the transients are a little bit late, and it's constantly moving backwards and forwards depending upon what's happening in the past and what's happening in the future. So instruments are modulating the timing of other instruments. And that again causes you problems with the brain because it cannot separate individual entities out. So this is a simple illustration of the timing problem. We've got a simple sine wave burst. So it's 0 and then it suddenly starts. And if we sample at this point here, the first sample will be 0. And then we sample it there and it comes through there. And you can see that the transient is building up. So this is the actual digital data you'd get from the output of the A to D converter from this analog waveform. So if we put that into a conventional filter, an IR filter, a NOS filter, an MQA filter, all these minimum phase nonsense filters, you will get this. That looks nothing like that. It's lost the initial transient. That timing error is 100 microseconds. That is a huge error. And this is why those kind of filters sound soft, because transients are being removed. And if you can't perceive a transient, things sound unnaturally soft. Some people like that because it's hiding the noise floor modulation that the DAC is creating. So using one problem to solve another problem. But you're not really doing that. You're just on a superficial level solving the problem. What you need to do is to eliminate your noise floor modulation and eliminate the problems you've got with transients. And then you get a much better sound quality, which is what my approach is. How do we get to recover what was the original? You can do it and it's called something called a sync function filter. This has an infinite amount of processing in the ideal sense, and the beauty of the sync function filter is that it will actually reproduce this initial starting point when the data was 0. And it does that because it pre-rings and post-rings. And the summation of all these different ringings gives you this thing. So a sync function filter will perfectly reproduce the original bandwidth limited signal. It will be completely identical. No transient problems, no timing problems, everything will be perfect. But of course, there's a catch. It needs an infinite amount of processing, and it would need to do it from the start of the time of the universe started to when the universe finishes. So it's kind of not very useful for us. So theory is clear. If we have an infinite amount of processing, then the DAC will perfectly recover the transient timing. But there are ways around this problem, and that is to make your filter algorithm do its best job with the amount of processing that you've got to recover the timing instrument, the timing information, or remove the timing uncertainty. And that's how we come to the WTA filter. This was first started in 1999 with the DAC64. It had 1,000 taps. Taps tell you how much processing the filter is doing. So one tap is one going into the data. That's why it's called a tap, because you're tapping into the data stored in memory, multiplying it by a coefficient, and then adding through all the other taps that you're doing, and then you accumulate the lot together, and that gives you the next sample that you're trying to calculate. More taps you've got, the more accurate you're going to get the reconstruction. If you double the number of taps and keep the algorithm the same, your reconstruction accuracy will improve by a factor of 2. Problem is, the ear or rather the brain is incredibly sensitive to these timing errors. And again, one of the things I've been able to do with COVID is to be able to get a handle on how much we need to do to improve the situation. And the number is a scary number. And that's something I'll be talking about next year, when I come here next year. So, it's been optimized by doing lots and lots of listening tests. So the way it was driven on this was partly theory, and mostly by just changing things, listening to it, changing things, listening to it, and listening to different parameters: instrument separation, focus, the timbre variation, the pitch definition, the sound stage, and then optimizing the filter, and keep changing things so that things actually improved. It was very, very sensitive. Eventually I was listening down to 10 parts per million on the windowing function. That's an incredibly small number. And that's why it's taken many, many years to optimize the WTA algorithm. Mojo 2 has over 500 times more processing power than a regular chip DAC. So it reconstructs transients to a much greater accuracy than regular chips. What does that give you in terms of sound quality? Better pitch reproduction, particularly bass. You can follow the tune of the bass guitar much more accurately. Easier to hear the location of instruments in space. Its instrument timbre is much more varied. Instrument separation and focus is much better. And you don't get listening fatigue. Listening fatigue is a real major bugbear with digital audio. In the past, I could listen to my music for about an hour and then you just want to stop. With my DACs, you can listen for 10 hours. Get off the plane, go into your hotel room and play the music again. You don't get listening fatigue. And that's a huge benefit. So I've talked about the basic theory, and what I've talked about applies to all of the DACs from Mojo 2 right up to Dave. Of course, the better the DAC, the more expensive the DAC, the better I'm able to improve on these factors. So I'm going to talk now about Mojo 2's improvements over the original Mojo. Improved FPGA functionality, and to do that I needed to have more power in the FPGA. So on the original Mojo, I used about a third of the capacity of the FPGA. And I had to do that because I was limited on power. So the size of the case of Mojo meant that you could dissipate about 1.8 watts, and if it was higher than that, it would get too warm. And the other factor is your battery gets depleted if it's too high. So we wanted to improve the battery life and reduce the temperature. So it meant that and to improve the sound quality. So I had to do savings on the analog section in terms of power, and then spend that power budget on the FPGA. And that's what I did. I actually made savings of about 300 milliwatts, and the FPGA power dissipation went up by 250 milliwatts, and the battery capacity went up by 9%. So we ended up with a lower temperature, much more capable processing, and longer battery life. And now I'm using 98% of the capacity of the FPGA, and that's given me lots of benefits. The other thing that Chord wanted me to do was to get rid of the coupling capacitor that was inside Mojo. We use a DC server on Hugo 2. That requires about 50 milliwatts worth of power to do all that. But then I had a problem, because I used that capacitor to give Mojo's original warmth and slight soft sound that Mojo had that everybody liked. So now we've got something that's more like Hugo 2, which is more neutral sounding, but how do you get back the warmth? Which is a particular problem if you're using inexpensive transducers, which tend to sound a little bit bright. So I thought, we need to have the ability to adjust the sound, which means EQ. But the problem with EQ is that when you listen to EQ with a 64-bit PC, the sound quality and the transparency gets degraded. I designed IR filters, and IR filters is the way you do EQ, called biquads, in the past, and there were immense problems with IR filters. But it was something I could fix. So what else did we do? So I added this DSP core, the UHD DSP. We're getting a more neutral tonal balance because of the DC coupling. Improved sound quality was one of the things I wanted to do with better transparency. To do all this, to control it, we needed a menu switch, which is backlit. The other thing that Chord insisted upon, in fact there was only one thing that Chord really insisted upon, it had to be the same size and it had to be polycompatible, for obvious reasons. So Mojo 2 is now DC coupled with a digital DC servo. That makes the bass sound a lot tighter, the overall sound more neutral and leaner. The WTA filter's been improved. The original Mojo was 38,000 taps. This is now 40,960 taps. But there's been other improvements inside the internal architecture of the WTA filter. It's bringing it up to the modern standard rather than the standard I was using in 2015. Improved noise shaper. That gives you better, more accurate reproduction of very small signals. That gives you better detail resolution and depth. Improved 4-element pulse array DAC. What I was worried about was distortion at very high frequencies. This is above 20 kilohertz. There was a little bump in distortion from 70 kilohertz, around 70 kilohertz to 200 kilohertz, which is not present on all the other DACs. And I knew the reason why it was there, and I wanted to remove that, which caused other problems, but that's another story. As a consequence of that, there's lower out-of-band noise on there as well, which makes it sound a little bit warmer. So how do we change the tonal balance without degrading the transparency? This leads us on to the UHD DSP. Existing DSP does not sound transparent. So you can easily test this. If you get up parametric EQ on your PC, graphic equalizer rather than a parametric, increase each band by 1 dB. and reduce your volume by 1 dB, and then listen to the sound with the EQ off and putting your volume back again, you will hear quite a substantial difference. Noise floor modulation is present. Things sound brighter and grainier. The soundstage collapses. It sounds flat and unengaging, and it's just not transparent anymore. Problem with this is that the small signals are losing the amplitude accuracy. One of the other things that I found, and this was a result of trying to figure out why the M scaler, when you plug an M scaler in, the depth suddenly improves quite markedly. And this was a big puzzle to me, because whenever I'd made improvements to the WTA filter, it had never changed depth. But with M scaler, it suddenly did. And it wasn't about small signal amplitude, because that's nothing to do with the number of taps. That's to do with the way the internal processor is actually being quantized and the noise shaping that goes on. That's something else, and that's fixed. So it meant there was something else that was defining depth that wasn't small signal amplitude related. And it must be a timing related issue, because that's what the WTA filter changes. It changes the timing. And I had this idea, I could detune a noise shaper and measure it and do some listening tests. So I detuned a noise shaper and adjusted it, and then listened to it. And by adjusting this detuned noise shaper, I could tweak it and hear the difference in the sound. And I did this quickly, didn't do any simulations work, it was just a rough test, see if something made a difference. And I selected number 3. Number 3 was the setting which sounded the best. Number 4, the depth degraded. Number 2, the depth degraded. Number 1, the depth was bloody awful. It was flat as a pancake. So I thought, oh, this is interesting. So now I've got this subjective number. Let's run my simulations and find out what this thing is doing. At minus 90 dB, there was absolutely no difference between any of the settings. At minus 120 dB, there was no difference in any of the settings. They were all measured exactly the same. At minus 301 dB, I could detect substantial differences. The amplitude was perfect on all the 4 settings, but the timing, the phase shift was different. So when you compare 0 dB against minus 301 dB, there was a delay, and the delay was different for the small signals. The worst one, the delay was 2 microseconds. The 2 middle ones, number 2 and number 4, it was 100 nanoseconds. The good one was within 10 nanoseconds. So you could hear 10 nanosecond shift to 100 nanosecond shift for a signal at minus 301 dB. And I didn't know these results when I was doing the listening test. It was just, I just did the listening test quickly and played with it, and I could select the one. And I selected the one that was exactly spot on. The weird thing about this is, how the hell can the brain detect 100 nanoseconds at minus 301 dB? Because that's just plain nuts. Now, with UHD, with DSP, you've got a huge problem, because filters are biquad filters. And a biquad filter, you multiply the incoming signal by, for when you're doing bass, for example, you multiply it by a very small number. 2 coefficients are set to very low levels, and the feedback coefficients are set to higher levels. When it gets done, it then gets truncated, and then it gets fed back and amplified, and fed back and amplified, and fed back and amplified, and a small area becomes bigger and bigger and bigger. And the problem is that small signals are treated differently, because at very small signals, the IR filter can't track the signal, and it loses the signal, and it no longer filters. So you get a phase shift because it's not working. So micro signals get this phase shift that you don't have for large signals, and this is a huge problem with DSP. The other issue with conventional DSP is its floating point. And floating point by its nature creates noise floor modulation. A 64-bit floating point is 52 bits, plus the rest of it is the mantissa. That innately changes the dynamic range with signal level. That creates noise floor modulation. Okay, this noise floor modulation is at minus 300 dB, but that's audible, very audible, because I've done tests before where I've heard noise floor at minus 400 dB, and it's still audible. And that explains why when you play around with 64-bit floating point, things sound brighter than they should do because of the noise floor modulation, even though it's very, very small. So what specs do we need for a fully transparent equalizing DSP? It must reproduce minus 301 dB perfectly in terms of amplitude. It must reproduce it perfectly in terms of phase, so there's no phase shift within a thousandth of a degree. And we know this because that's essential for depth perception. And of course, it must not have noise floor modulation, which means it cannot be floating point. Now, I ran all this, did some calculations on the back of an envelope, worked out I needed it to be 104 bits. Ran it, did some tests. It failed to reproduce minus 301 dB in terms of phase. It managed it with amplitude, but it didn't do it in phase. And then I realized I had to put noise shaping in to improve it. So even though it's 104 bits is still not good enough if you were to use a conventional architecture. Well, the way a noise shaper works is you get an error. That error goes into the noise shaper remembers the error, feeds back, and it gets reduced for the next sample. Whereas in a normal digital processor, the error is discarded and you've lost track of the error. So a noise shaper is a feedback mechanism that recovers the error and corrects for it. But the downside to that is you must run at a higher oversampling rate, which is why the DSP runs at 705 kilohertz, RAM 44.1. You cannot use noise shaping at 44.1 because it's not going to solve your problems at 20 kilohertz. And it's a particular problem for bass because, as I mentioned before, the coefficients are very, very small for bass. So to ensure transparency, it's got to reproduce minus 301 dB. And as I said earlier, jumping ahead of myself, the 104-bit design failed. It didn't do the phase shift correctly. And the solution was to noise shape it and noise shape each individual node separately. And that eliminated the issue, and it then passed the test. And we can see the plot for this. So this is a digital simulation. Now, we use the term simulation, but it's not a simulation. This is the real output. It's not like a pretend, a model or something. This is what the thing will do. And I can actually do this in real life in terms of measurements, and this is the way it would perform if we were to do it as a digital measurement. And we can see that the minus 301 dB signal, this is the FFT that the computers calculated from the data, is perfect at minus 301. It's within a thousandth of a dB, and the phase shift of that is within a thousandth of a degree. What I did with this was to run it so that there's plus 9 dB on the 20 hertz and minus 9 dB at 20 kilohertz, and I used a 6 kilohertz sine wave, which is what I always use for doing these kind of tests. This means that minus 301 dB is being perfectly reproduced in terms of phase and amplitude. So what features have I got on this new DSP? I've increased the range on the volume control because one or two people were posting saying very, very sensitive IEMs. I want to turn the volume down a little bit lower, and it's just still too loud at the very low settings. So I've increased it now. You've got minus 108 dB going up to plus 18 dB. There's an indicator to tell you there's a high volume setting and a low volume setting. You've got obviously the bass tone controls, which is a peak controls with a Q of a half set to 20 hertz. There's a bass shelf. Now a shelf works, it boosts everything below 125 hertz right down to DC. And you can go up to plus 9 dB or minus 9 dB, and you can set each individual tone to 1 dB. Treble 3 kilohertz shelf, again, this is going 3 kilohertz up to 384 kilohertz in this case. And then there's a 20 kilohertz peak control again. I used a Q of a half so that it was easy to remember. If you peak it at 20 kilohertz, 10 kilohertz, exactly half the number. And you need something fairly broad because this is a broad tone control. It's not something that's designed to remove specific resonances of headphones. It's to give you an overall shift. It does work very well in terms of bass. You can pretty much compensate for any bass problems that a headphone has got. But if you've got a 6 kilohertz resonance you want to null out, forget it. This is not what the intent of this thing is to do. It's there to make it sound warmer, smoother, brighter, more incisive, for you to tweak it to suit what you want. We've also added the crossfeed. Now I love crossfead. With Hugo 2, I can't run without the crossfeed because it improves the sense of the sound coming out outside of the headphones. On Hugo 1, I didn't have that sense, so I used crossfeed because I didn't like LCR, that's what they call in pro terms mixing, where it's left, centre, right, Beatles sounds, and things being that way. I like it that way. But it never really gave you that out-of-head experience. Hugo 2, the depth perception and the detail resolution was much better than Hugo 1. And you could hear an improvement in depth when you put crossfeed on. Mojo is more like Hugo 2 than it is Hugo 1, in that because the small signal accuracy is so much better, when you press crossfeed on, you do get a better sense of depth. There's also a high frequency filter. The benefits of doing the high frequency filter with DSP is that you can make it completely flat at 20 kilohertz. And that's permanently on, and that improves the sound quality on all sources, particularly 96 kilohertz and 192 kilohertz recordings. So the sound quality benefits of the UHD DSP: no loss in depth perception when you're using it. Detail resolution is preserved. Timbre reproduction is better. Instrument separation and focus is maintained. If you want it to sound a little bit warmer, it's easy to do. If you want it to sound brighter and more incisive, it's easy to do. So you can tweak the sound to suit. You can compensate for the bass performance of your headphones. If you've got a sibilance problem, you can just dial down the 3 kilohertz, and that will fix that. I'm not going to go through the menu settings because I want to make sure we've got time for question and answers. I will be publishing this. It's already on Headfire, but I'll be publishing this presentation on Headfire again. I'm not going to go on the volume control, but this gives you a quick chart. If you press positive and negative together, you'll get a mute. This is the crossfeed settings. It's fairly obvious. Tone control settings. We spend a lot of time, or I spend a lot of time, trying to make this intuitive and easy to use, and I think we succeed. Based on the reports that people have come back and how easy it is to use it. You've got a lockdown setting as well. Measurements. This is fairly important to me because I like to say I'm not a bullshit merchant. I'm not trying to sell you something. I'm trying to give you the facts. The measurements prove what I'm saying isn't bullshit. So, dynamic range 125 dB, that's pretty much the same as the original Mojo. Distortion and noise is pretty much the same. In fact, all those measurements are pretty much. The big difference is the stereo separation. 118 dB which is a lot better than original Mojo, and that's because the power supply isolation is better. And the reason I did that was so that when you're in permanently running it, the battery is isolated, so it requires the power supply to be better regulated to stop that problem. Noise floor modulation, again, there's no noise floor modulation, and this is the proof of it. As you can see, turn the signal off, same noise floor. Noise floor is minus 177 dB. Distortion levels are pretty low. And this is interesting, small signal accuracy. You will not find this on any other DAC at any price. That's a non-chord DAC. This is actually the left and right signal superimposed. You can't see the difference. 16-bit level there is perfectly reproduced. These ringing is what you'd expect. That it has to have that ringing because of the nature of what we're doing. So that's a perfect reproduction of a 16-bit signal. And that's state-of-the-art performance. There's only two DACs better than this, and that would be slightly a TT2 and slightly a Dave. I'm not going to talk about batteries because I want to do question and answers. Talk about the summary. When Mojo was launched in 2015, it was an amazing success. Chord sold large numbers of Mojos, which is pretty amazing for an exclusively audiophile product. Mojo 2 builds upon the success of Mojo, but I've made the improvements that I've talked about. In short, it's state-of-the-art transparency and musicality. And by musicality, I mean being emotionally involved with the music. That's what it's all about. And of course, we've got a good DSP. So please, questions. Yes?
I was hoping you could maybe explain in more detail what you mean by transparency. Are you talking about transparency to the original performance or to the original recording? Which isn't necessarily the same thing, especially if you're looking at digital recording.
That is an incredibly good question. Yeah. And it's something that always bothered me. What the hell are we hearing? I wasn't there for the original recording. Don't know what the acoustic sounds like. Don't know what the recording engineers did. Don't know on the microphones. Don't know anything. How can we actually make any sensible assessment of sound quality when we don't know what we're listening to? And right at the very beginning, I talked about variations. The other issue is you may be doing something that's improving the sound quality, but it's actually a distortion. Like I was talking about transients. You blur the transients, things sound softer, that hides your noise floor modulation problem. The escape out of that problem is about variation. So often I've listened to something and thought, that sounds more transparent because it's brighter. And it's actually turned out not to be more transparent because it's got a little bit more noise floor modulation. And that lulls you into a feeling it's more transparent because when you get noise floor modulation, things sound crystalline and clear, but it's artificial. But it's the variation that is the killer. So if things are more varied, if bright instruments sound brighter, warm instruments sound warmer, the dynamic variation is more expressive. So what you're trying to do is listen to a recording, evaluate the instrument separation and focus, evaluate the timbre variation, evaluate the space. Is there more variation in space? If it ticks all those boxes, in that it's more expressive, there's more variation, you know you've made a fundamental improvement. And it doesn't matter whether you don't like the sound or not. That's irrelevant. Generally do like the sound when it's got more variation, but it's not about the quality of the recording and it's not about the quality of your system. More variation, the better the thing is fundamentally. The other benefit that I've got is that all of my, the vast majority of my listening tests, particularly now, in the beginning it wasn't like this, but now I am looking at a specific aberration, which I can measure. I can measure minus 301 dB in the digital domain. I can find out what the phase shift is, and then I can listen to it. Much of my A/B listening tests are about identifying an error that's in the digital domain, which I can quantify and measure, and then reducing it, and keep on reducing it until I can no longer hear a difference. And that's the crazy thing. When I keep reducing it to no longer hear a difference, we end up with incredibly small numbers. The most guaranteed best listening test is when you can hear nothing at all in terms of the change. When you know you're making a tangible difference and there's no difference, because there's no then question about whether this is a real improvement or not a real improvement. You're not having to evaluate that. So does that answer your question?
Well, I guess are these concepts and the technology and kind of principles and algorithms you're working with, are they things that can be applied to analog to digital conversion as well as digital to analog conversion?
Oh, of course.
Better analog to digital conversion solve a lot of these problems.
From an A to D and a D to A is actually the same from a mathematical point of view. It's just you have analog integrators rather than digital integrators. You still have a DAC in an A to D and in a DAC. And I am working on an A to D converter. In fact, I mentioned 6 months ago that I was testing one and it actually didn't work, so I'm respinning it again. So I seem to be fated on the A to D converter. This is the 4th iteration that has failed because of nothing to do with A to D, but actually due to power supply issues. So yes, A to D is something that's really important. Any more questions? Yes.
On the subject of transients, I think you mentioned between samples about 22 nanoseconds or microseconds?
Microseconds, yeah.
Is that at a 44.1
yes.
sampling rate? So if you increase the sampling rate, does that get smaller?
Yes.
So that will help with the transients?
That helps with the transients. Okay. In fact, if you double the sample rate, the area of the error reduces by a factor of 4. And if you keep doubling it, it's 4 times better. So when you're getting to 705 kilohertz, you're 256 times less error, which is quite substantial, which is why 16fs or 705 kilohertz is the sweet spot. When I do look at the WTA2 filter, it's much less sensitive to tap length than the WTA1, which is the one that takes you from 44.1 to 705. In fact, I actually know that above 64 fs it becomes almost unimportant. I mean, it is important, but that's another story. In terms of timing accuracy, in terms of the sync function, it becomes unimportant. It's a complicated situation. It's a very complicated situation. But yes, it would be wonderful if all our recordings were 768 kilohertz, because things would just sound, you wouldn't need scalars. Things would just sound amazing. And the 768 kilohertz recording that I have heard sounds like an M scalar. That's the future. But persuading the pro business to do that is going to be impossible in the short term. Yes?
So the observations you made about the behavior of the signals, does that apply to just PCM or does that apply to DSD as well?
Oh, DSD is a nightmare. DSD, you're looking at 10 microseconds worth of phase shift errors. You're looking at huge amounts of noise floor modulation. DSD64, the noise floor modulation is from 130 dB to 115 dB. So it's huge. So that phase shift problem I was talking about, that's the reason why DSD sounds soft, because it's not reproducing transients properly. There's not enough pulses available to accurately reproduce transients. It won't reproduce minus 140 dB, let alone 301 dB. because the noise, that's below the resolution floor of the noise shaper. DSD 256 is better, DSD 512 is better, but they've still got fundamental problems. All DSD, because of the 1 bit, will have noise floor modulation. I did a figure on the back of an envelope, and to get something like half decent performance, you'd have to be DSD 16,000, something like that. But yeah, that wouldn't solve the noise floor modulation problem. That's a fixed issue. So DSD is a disaster. The nice thing about DSD, you put DSD on a crappy DAC, it sounds okay. You put PCM on a crappy DAC, it sounds crappy. But you put PCM on a performing DAC that solves all these issues I've been talking about, which no other DACs do, it will sound spectacular, sounds much closer to the original live recordings. So PCM is potentially unlimited in performance if you get your DAC right. DSD is good, well, not good, but moderate for everything. Yeah. Oh, yes, you know, 3 minutes to go. I thought you were asking a question. Yes.
I think you said, like even on Head 5 with the old Mojo, that you found optical to be better than USB?
It's not quite as simple as that.
Okay.
Optical is the best input. USB can sound as good as optical. I've had situations when they sounded identical. Generally in a mobile environment, when you've got a mobile source and a mobile Mojo connected to nothing, it doesn't matter. USB and optical sounds the same. It's when you earth Mojo and you're using an earth source that the USB issue becomes important. The USB in that case would sound brighter and slightly more aggressive than optical. Optical would sound warmer. So that's why on the desktop DACs we always use galvanic isolation on the USB. Mojo and Hugo 2 does not have galvanic isolation, but the galvanic isolation is sort of 99% effective. It's not 100% effective. So on some sources that are not very noisy, you're perfectly fine. On very noisy servers, you will not be perfectly fine. You will hear an improvement with optical. So my go-to position is always use optical if you can, but it depends on the source. Some, my MSI laptop, optical and USB on the M scaler sounds identical. My MSI-based desktop computer, which is a huge computer, the optical sounds a lot better. So it all depends on your circumstances, on your system. But USB fundamentally can sound the same as optical. It's just a question of the circulating RF noise currents that's the issue.
So do all those just hold true with Mojo 2 as well?
Yeah. The USB is pretty much the same on that.
Can I ask a follow-up question?
Yeah.
What was the design decision around the buttons no longer rotating?
Oh, that was nothing to do with me. So
Design is
no, it's they would be forced into doing it because there's 4 buttons. You have to do a cylindrical because the depth is the same. If you're going to make it smaller, you have to turn it into a cylinder rather than a round ball. So that's the physical reason why it is. But I think they prefer it if it doesn't rotate anyway, because it's a more elegant solution and it's less likely to rattle. So yeah, I think it's a better solution. But I don't really care. It's not my domain. That's
You seem to get more dirt in there too whenever those can rotate, because then whatever finger oil
that's true.
collect on there as it rotates goes
that's
into
true.
the base.
Yeah, that's true. Yeah, and be careful when you're cleaning it.
Yeah. Send it to me, I'll clean it.
Yeah, we know one circumstance where somebody used some nasty solvent fluids and it needed a board replacement. Yeah.
So unfortunately we've run out of time, but I'm sure Rob would be happy to continue the conversation over at the Chord booth
Absolutely.
on the floor. So I strongly recommend everyone go over there and actually get a chance to listen to the Mojo 2 when he's still in. So thank you.
Thank you.